Hey, so welcome to Algebra 2. This is going to be section 7.3. This is what we're going to be calling removable discontinuities. We're going to find holes in our graph. So let's go ahead and let's start taking a look at some of the examples. So what we have right here is I've got three examples set up. Our first example for removable discontinuities is going to be, by the way, this is 7.3. Our first example that we have is going to be what happens when f of x is equal to x plus 2 divided by x plus 2, x minus 3. So if we remember with a rational function, when we have an x on the top and an x on the bottom, we know that the graph is going to be somewhat like this. We know the graph is going to have two parts, and it's going to be above and below opposite ends. If we have more than one power, meaning if we had several aspects right here, we might get something so neat as where it would bend back down and it would bend back up. And we just see that pattern repeat again and again. So let's take a look at this one right here. A removable discontinuity is the fact that our first thought when we try and simplify this is I have an x plus 2 up top and an x plus 2 on the bottom. So that means that I can take this graph and I can get rid of each x plus 2, and my new graph is f of x is 1 over x minus 3. And this is actually what I'm going to graph. The whole is that x cannot equal negative 2, even though we've simplified it. Because with the original graph, it had an x plus 2. If I plugged in x minus 2, that would be equal to 0, and I cannot 0 divided by 0 times, let's see, negative 2 minus 3 is negative 5. I cannot divide by 0. 0 divided by 0, it doesn't work. So no matter what I do, I cannot plug in an x equals negative 2. Let's go ahead and let's graph this thing. F of x equals 1 divided by x minus 3. So f of x equals 1 divided by x minus 3. Now, one of the first things that we remember, let's see if I can't zoom in here. There we go. The first thing that we can remember is the fact that we want to find our vertical asymptote. Our vertical asymptote is going to be found where the bottom cannot equal 0. Here I know if I set x minus 3 equal to 0, x cannot equal 3. Different than our original equation, it would appear as though I would have a second vertical asymptote at x plus 2, but that's not. That is our whole. Or the whole point of this lesson, the removable discontinuity. There cannot be an x equals 3, and there cannot be an x equals negative 2. X can't equal that, x can't equal that. Now, fortunately, because the power is higher on the bottom, there is no horizontal asymptote so far as just y cannot equal 0. We don't need to figure out what it is, we just know it can't be at 0. So knowing these three things, let's set up an xy table. My vertical asymptote, x cannot equal 3. So if 3 cannot be plugged in, I know that's where my graph splits. So I'm going to plug in some numbers to the right of 3 and some numbers to the left of 3. So 2, 1, 0, 4, 5, 6, and see what I get. Well, I have a 1 over 0 minus 3 is negative 3. So that's negative 0.3 repeating. I have a 1 over 1 minus 3 is negative 2, or negative 0.5. If I plug in a 2, that's 1 over negative 1, or negative 1. On the other side, if I plug in a 4, 4 minus 3 is 1. 1 over 1 is 1. Plug in a 5, 5 minus 3 is 2. 0.5. If I plug in a 6, 6 minus 3 is 3, or 0.3 repeating. And we notice because we have a 1 up here, and because this hasn't been shifted all over the place, we get some nice even values that repeat themselves. So let's see what that looks like in the graph. So we're going to build ourselves a nice graph. Hopefully I can stay on the lines next time. I have my X and I have my Y. I'm doing these by ones. 2, 3, 4, 5. 2, 3, 4, 5. Because assumed by ones, I don't need to write those out, but I'm just going to get in the habit of doing it. And I'm going to plug in these values into here. I'm going to do them in a different color so we can spot them a little easier. Let's do it in orange. So first off, sorry, my video cut out there for a second. So first off, I know I have a vertical asymptote, x cannot equal 3. So over here on my graph, I'm going to draw a dotted line. Because I know x cannot equal 3. Second off, I want to make sure that I include that hole after I'm done with the graph. But I'm going to go ahead and graph my horizontal asymptote where y cannot equal 0. That is on the axis, so that's going to be a little difficult to see. Y cannot equal 0. So I have my two asymptotes. And so now, in a different color, I'm going to go ahead and I'm going to graph these points right here. So I'm going to graph 0, negative 0.3, 1, negative half, and 1. Over here at 4, put that centered, I have 4, 1, 5.5, and 6.3. We notice the shape of this graph is that first type that we were expecting. It has two bounds. Now, one of the things that we know is that if I were to continue this graph in this general direction, my hole is somewhere along this vertical line. So I know the fact that I am going to have a hole at -2, and my graph is going to continue through it as though it doesn't exist. It's going to be, I shouldn't have put the arrow right there, but it's going to continue on the left side of it and on the right side of it. And we could actually test that by plugging in smaller and smaller and smaller points as we get closer to that -2. But we just know that there's going to be a hole in the graph right there. So let's move on to the second example. Now the second example is going to be, let's say an h of x is equal to x plus 3, x minus 1, x minus 4, x minus 1. Okay. And if we look at this and we remember what we just talked about, I know my first thought when I see x's on top and on bottom is I know I'm going to have a graph that's got this sort of shape, either like we saw before with the above and below, or if there's multiple ones, we might see a triple rational. So let's take a look at this. And I know I'm going to have to find a vertical asymptote. I know I'm going to have to find a horizontal asymptote. And I know most likely because of the section we're in, I'm going to have to find a hole in the graph, but I don't know that just yet. These are the first two things I look for. And when I look at this, I see the fact that my vertical asymptotes should be right here, where I should have an x can't equal 4 because it would make that equal to 0. I know I shouldn't have an x can't equal 1 because it would set that equal to 0. However, you notice that I have an x minus 1 on top and bottom, so that is not an asymptote, that is a hole. So we're going to move that down there and take it away from this aspect. And unlike the one before, because I have an x on top and bottom this time, my horizontal asymptote is found by the ratio of their coefficients. So the ratio of these coefficients is 1 divided by 1, so y can't equal 1 over 1, or just y can't equal 1. And that's all the information I need to graph it. Vertical asymptote, horizontal asymptote, whole. Our simplified graph that we are graphing is x plus 3 over x minus 4. We're going to graph that over here. Let's write that on our graph paper. For 2, I have h of x is equal to x plus 3 over x minus 4. I have a vertical asymptote. X can't equal 4. I have a horizontal asymptote. Y can't equal 1. And I have a hole in my graph where x can't equal 1. Even though I could plug in a 1 and get a value, because originally, on our original problem, if I plugged in a 1, I would get a 0, and I cannot divide, even if it's a 0 up top, I cannot divide a 0 by 0. It would void the equation. So I know the fact that I'm going to have to skip over the 1. I can plug it in, but it's not going to be part of my graph. So let's see what that looks like. If I have an XY table, I know that my first asymptote is at 4, so I'm going to plug that right in the center of my graph, and I know that 4 is that vertical line that we saw earlier. I'm not going to be able to plug anything in because I'm going to get an infinity. So I'm not going to plug in 4, but I'm going to plug in the numbers on each side of it. So 5, 6, 7, and then 3, 2, ooh, can't plug in 1. There's going to be a hole right here. So whatever answer I get, I know I'm not actually going to include in my graph. So let's see what we get. Let's plug in a few numbers. If I plug in a 5, 5 plus 3 is 8. 5 minus 4 is 1. If I plug in a 6, 6 plus 3 is 9. 6 minus 4 is 2, or 4.5. If I plug in a 7, 7 plus 3 is 10. 7 minus 4 is 3, and that's what? 3.3. We notice how it's going down in this end. Let's plug in these values over here. If I plug in a 3, 3 plus 3 is 6. 3 minus 4 is negative 1. Did I do that right? Let's double check. Let's plug in a 5. 5 plus 3 is 8. 5 minus 4 is 1. 8, yeah, okay. 3 plus 3 is 6. 3 minus 4 is negative 1. Negative 6. Okay, cool. If I plug in a 2, 2 plus 3 is 5. 2 minus 4 is negative 2. That's going to be a negative 2.5. Oh, there we go. I had it backwards in my head originally. And now the 1, I'm going to plug this in, but I know, like my previous one up top, it looks like I'll get a value, but I know per my original graph, I can't include it. So I'm going to draw a circle, and I'm not actually going to include that as part of my line. So let's plug in a 1. 1 plus 3 is 4. 1 minus 4 is negative 3. It's going to give me negative 1.3. And that's all I need to graph it. So let's move over here and let's graph it. I'm going to zoom out a bit so we can see some more of the information. I have my x, I have my y. I need to go down to negative 6. Do I have it for ones? 1, 2, 3, 4, 5, 6. Yeah, I can get there. I need to go up to 8. So my y is going to be by 2's. So 2, 4, 6, 8. My x, I need to go up to 7's. 1, 2, 3, 4, 5, 6. And I'm going to do that by 2's as well. So 2, 4, 6, 8, 10. That way they all fit. And the first thing I'm going to do is I'm going to include these values right here. I'm going to include a vertical asymptote where x can't equal 4. So over here, I'm going to draw a vertical line. X cannot equal 4. I have a horizontal asymptote where y can't equal 1. And that's going to be in between my cells right here. Y cannot equal 1. And I know eventually I'm going to have my hole that I'm going to draw a circle as part of my graph. Let's go ahead and let's graph the other points. So we can zoom in a little bit more. If I start on the right-hand side, 5, 8, so 5, 8, 6, 4.5, and 7, we go up to 2, it's roughly right there. So now my graph is going to look something like this. And on the other side, when I go to the left, I am going to have a 3, negative 2, negative 4, negative 6, 2, negative 2.5 roughly, and then a 1, negative 1.3. But remember, this is our hole, so I'm not going to include it as a point. I'm going to draw it as an open circle, because we know that the shape is going to remain unaffected. The graph doesn't actually include that point, it skips over it. It's kind of like how you felt in dodgeball class when everybody was getting picked along the line and they just kind of skipped over you. That's exactly what a hole is. We're moving in a continuous fashion and we just skip that one little point right there, but the graph doesn't look any different than it would before. So that is basically what a removable discontinuity is. At this point, I think you've got the basic idea. I'm going to do a third example here for one that has a triple asymptote as opposed to being the 2 and the 2. We're going to see the 3 part. But I think this is a good stopping point if you just wanted to get a rough idea of what an asymptote is. So let's continue with the third if you want to push forward with that. I'm going to zoom in. I'm going to draw example 3. Example 3 is, let's call this g of x is equal to x minus 3. This is a big one. X minus 3, x plus 5, x minus 1. And now the reason why this is different than the ones above is we notice how when we simplified the ones above, we had one with an assumed horizontal asymptote. We had one with a found horizontal asymptote. And now this one is also going to be an assumed because we notice that these are going to cancel out. There's not going to be anything up top. So let's go ahead and let's start out. Our vertical asymptotes should be x can't equal 3, x can't equal negative 5, and x can't equal positive 1. Those are our 3 vertical asymptotes. We already notice something about one of them, what it's going to end up doing. Our horizontal asymptote, as we said, just like the top one, where after we reduce it, we have a 1 up top, it's going to be an assumed, running out of paper here, y cannot equal 0. And then my hole is anything that I can cancel out of my vertical asymptotes. And let's take a look and say, can I cancel anything out? I have an x minus 3 and an x minus 3. That cancels out, which means that that horizontal or that vertical asymptote has now been moved to a hole. X can't equal 3 is just a single point, not an asymptote. Cool. And so our new graph is going to be 1 over x plus 5, x minus 1. And now this is the easier way to graph it. You might end up seeing it, and we know that this is an equivalent expression. X squared, 5x minus 1x, so that's 4x minus 5. You might see something that looks like this, and we know we'd have to factor it to get down to here. I'm just going to leave it in factored form because it's easier to graph that way. So let's go ahead and let's take this, let's move it over to our graph paper, and let's graph it. So for our last example, running out of room. Let me fold this. Okay, so for our last example, example 3, we have, what was this? G of x is 1 over x plus 5, x minus 1, because we're doing the simplified version here. We remembered we had vertical asymptotes, we had 2 of them. X can't equal -5, and x can't equal a positive 1. Let me get those. We have a horizontal asymptote, y can't equal 0. And we have a hole in our graph at x can't equal 3. So when we build our xy table, unlike where we only had one vertical asymptote, we had one spot where we're splitting the graph, that one spot where we're splitting the graph. Here we're going to have 2. So for my xy table, I'm going to make it a little bigger because I know at 1, I'm going to have a break. And way down here at -5, I'm going to have another break. And I'm actually going to do fewer points just because my video cut out again. I have low battery. Just because I know what the general shapes are. So we're going to save some time. So -5, I'm going to plug in -6 and -7. On the other side, I'm going to plug in a -4. To the left of 1, I'm going to plug in a 0. And I know that I'm going to connect these, whatever shape that they may have. On the other side of 1, I have a 2 and a 3. But remember that 3 is my hole. So we see we have 3 parts of this graph. I'm going to have part 1, I'm going to have part 2, and I'm going to have part 3. So let's see what we get. Let's plug in a few values here. I'll plug in a -7. I have 1 over, well, -7 plus 5 is -2. -7 minus 1 is -8. That is -2 times 8 is positive 16. So 1/16, which I'm going to have to bust out a calculator for that because I do not have that number off the top of my head. 1 divided by 16 is going to be 0.06. 0.06. I plug in a -6. -6 plus 5 is -1. -6 minus 1 is -7. 1 times 7 is going to be 7. That as well. That's 0.1. It's going up. If I plug in -4, -4 plus 5 is 1. -4 minus 1 is -5. That's 1 over -5, or -0.2. Plug in a 0. It's a 5 and a -1. Oh, it's just the positive version of that. Nope, it's the same thing. That's going to be a nice, easy parabola to draw because I know 2 spots on the vertex. I know the middle should be right between the 2. And if I come down here and plug in some higher numbers, if I plug in my 2, I have 1 over 2 plus 5 is 7. 2 minus 1 is 1. That's 1/7. Oh, look, I'm getting a mirrored image of this. I like these. I don't need to type it in again. If I plug in a 3, it's 1 over the bottom is 8. 3 minus 1 is 2. That's 1 over 16. Again, that's a mirror of the top. That's 0.06. Okay, so I've got my numbers right here. I'm going to move over here, and we're going to graph this. X, Y. Let's see, I need to go up to -7 and -3, so my X is going to be by 2s. 2, 4, 6, 8, 10. My Y, however, I don't have much of a spread right here, so I'm going to do y by, how about by half? So 1, skip 1, 2, 0.5s. So that'll give us some room to move around. X is by 2s, y is by halves, so every other one is a whole number. Let's see what this thing looks like. I'm going to zoom out so we can see those numbers a little bit better. Okay, -7, 2, 4, 6. Actually, first thing I'm going to do, I almost missed it, vertical asymptotes. 2, 4, 5. X can equal -5. And then 1 at 1. X can equal 1. And I know I have a y assumed right here. Y can't equal 0. So we see how this is going to have 3 parts. We're going to have a part on the right, part in the middle, part on the left. So the part on the left is at -7, so 5, 6, 7, 0, 6. So it is right here. And I know at -6, it's just a little bit higher. Doing this in a different color. So I know that this is going to be staying above, and I kind of touched it right there, but it's going to stay above this horizontal asymptote. I'm going to move to the middle section. So between these two, it's going to be these numbers. So at -4, -0.02, and at 0, I'm at that same value. So I know that this shape, again, it's going to have a nice little parabola shape right there because it's going to stay below this asymptote that runs across. This one's staying above, this one's staying below. Actually, I know where this one's going to be. Well, let's not assume. Let's go ahead and figure it out. 2, I plug in my number right here. And at 3, I draw an open circle because I want a point to be there, but it's a hole. Boom. And there we go. And that's a nice little triple graph. We have 2 vertical asymptotes. We have 1 horizontal asymptote. Graph, graph, graph. It looks just the same as before, but there's a single point removed. In fact, each one of these graphs looks just the same as before. It just has a single point removed. Even our top one. We didn't actually see it over here. We had to include it in. But each one of those things has a single point removed. So that concludes 7.3, finding a hole or a removable discontinuity. If you have any questions, feel free to contact me.